Hi, this is Robert White. I'm going to give you a short presentation on a MEMS microphone array on a chip that's been developed in my lab at Tufts University. The main student working on this project was Joshua Krause, and there's additional support from Zhengxin Zhao, Shuangqin Liu, Minchel Shin, John Burns, and support from Spirit Air Systems and Draper Labs. The goal of this project was to develop a MEMS pressure sensor array to measure the fluctuating pressure underneath a turbulent boundary layer in wind tunnel tests for free stream velocities up to 300 meters per second, so about Mach 0.9 or so. Our particular goal was to achieve a very fine pitch on the chip in order to produce high spatial resolution of measurement of the fluctuating pressures under the turbulent boundary layer. In order not to influence the flow, we wanted to keep the surface profile, that is the roughness, low, and we also wanted to manage the interconnects in a good way so that it wouldn't be too difficult to handle the large number of microphones that we would have on our chip. Just quickly, a brief review of flat plate turbulent boundary layers. If you have flow that starts out uniform from the left there and then moves over a flat plate, so coming in like this, a boundary layer will develop on the plate, and that boundary layer thickness will grow as the boundary layer moves down the plate. So it'll start out relatively thin and laminar, and then at some point it will transition into a turbulent boundary layer where there's vorticity and eddies of all kinds in this complicated turbulent region. Once you have a turbulent boundary layer, the pressures are no longer steady, they're now fluctuating. And so those fluctuating pressures produce forces on the surface which can cause vibrations and acoustics internally and externally to a structure such as an aircraft or an automobile. So our goal is to be able to characterize what those fluctuating pressures look like under turbulent boundary layers to provide information to designers who are trying to produce better structural vibration characteristics and acoustic characteristics for automotive and aerospace systems. One thing you should know about the turbulent boundary layer is that underneath the turbulent boundary layer there's a very thin viscous sublayer in which the flow is not turbulent, it's just not quite laminar, but it has very simple structure and it's not very turbulent. And if we can keep our MEMS structures within that viscous sublayer, then they won't have a major impact on the turbulence and they won't cause the turbulence to trip or change its properties. So we would like to keep our surface roughness less than that viscous sublayer, which is maybe about 0.7 times the free stream velocity. And this convection velocity is less than the speed of sound, and so that means that the energy of convecting eddies a lot of the energy lies along this convective ridge. Now, for a traditional microphone that might be measuring acoustics, the propagation speed is the speed of sound, c, which is larger than this convection velocity. And so more of that energy lies at long wavelengths, that is low wave numbers. But if this uc becomes smaller, more of the energy lies at high wave numbers, that is short wavelengths, and so you need to get your microphones closer together. So with a MEMS array, you might be able to span a larger region of this frequency wave number space, both going to higher frequencies, since your MEMS devices have a higher resonant frequency than traditional microphones, and also going to higher wave numbers because you can get your microphones closer together. In addition, we want to keep the surface topology low so we don't influence the flow. We need a large dynamic range because these fluctuating pressures could be quite loud. And then I've already said this, we need a large frequency range and a large wave number. So that's the main reason why we might think that MEMS arrays are a good idea. We're not the first people to apply MEMS microphones to the measurement of turbulence. There's a group at the University of Florida, Mark Sheplak, Lou Catafesta, and Toshi Nishida. Lou, I think, has moved to Florida State recently, but this group did a lot of work in MEMS microphone development, other kinds of aerospace sensor development, and has put them into arrays and done some measurements in wind tunnels and so forth. So they have a large number of papers, and they've done some excellent work. There's some other examples of this as well. So here's a group from NASA Langley that put commercial microphones onto a flexible sheet to create an array. Here's a group from Taiwan that put a few MEMS microphones together into a small array here. And here's another group, Burns, Buder, Omeyer, Walter, and Leader. Actually, I forgot which institution they're with, but they've put another group of commercial MEMS microphones together into this could be their own microphones, I'm not sure, together into an array. So the main difference between this prior art and the system that we've developed in our lab is that in all the prior art, individual microphones were made and then assembled together into arrays in the examples you just saw, whereas in our device we put all the microphones together onto a single chip. So we micro-machine the whole array as one chip. So our particular chip has a 64-element array, 8x8 array, on a 1 centimeter by 1 centimeter chip. The elements themselves are 0.6 of a millimeter in diameter, and they're pitched center to center by about a 1.25 millimeters. All the microphones have individual outputs coming to the side of the chip so we can individually receive information from every microphone in the array. The individual elements look like this. They're surface micromachined using the MEMS process, so they have a polysilicon diaphragm with a 2 micron air gap behind it. There are holes through the diaphragm to allow static pressure to equalize. There are bumps on the bottom of the diaphragm to stop it from sticking down. There's a backing electrode made of doped polysilicon as well, and when this microphone is excited by a fluctuating pressure, the diaphragm vibrates, this gap changes, and so if we set this up in a capacitive sensing regime, we will have current that flows on and off of this plate, and we'll be able to measure that current to get our signal. So this is a small condenser microphone. It has to be externally biased. So here's a microscope picture showing the device. The devices are fabricated using the MEMS process. Start with silicon substrate, put down a nitride isolation layer, put down a doped polysilicon layer, which is patterned to create the bottom electrodes, put down a 2 micron thick oxide, which is patterned to create the sacrificial layer. This will become the gap later on. Put some dimples into the oxide so that these dimples are now going to create those bumps in the corrugation in our diaphragm. Deposit additional 3.5 microns of doped polysilicon on top of this and pattern that. That becomes the top diaphragms. Then etch out the oxide, removing this sacrificial layer to produce this released diaphragm structure with holes through it and bumps on the bottom. And then finally, after we get this back from the manufacturer, we then deposit a parylene C layer on top of everything, which coats this, helps to protect it, and partially seals up these holes. We actually don't seal the holes completely, but we control their diameter in order to get the low frequency bandwidth, but not bring this all the way down to DC. So we don't want to make a barometric pressure sensor. We want to make a microphone. This is what the device looks like when it's finished. So you can see all the dimples and the holes in the diaphragm here. You can see the corrugation around the edge, which allows the residual stresses to relieve. It's anchored around here. We have one line coming into the top electrode, and then through this tunnel region we have a second line going into the bottom electrode, and so we have our 2 wires coming out. Here's an SEM image of the same thing. It's important to package this well so that we have low surface roughness. So this is our packaging process. We start with a ceramic pin grid array package. We fill the center of it with a high resistivity potting epoxy, let that cure, and then we use a computer-controlled mill to mill out a pocket in this, which is the right size for the chip. So it places the chip both in the center, aligns it, and gets it at the right height so that the tops of the chip will now be flush with the top of the package. We then put a small amount of epoxy on the back of the chip and pop it into this socket, so now it's aligned in there and mounted at the right height. We paint manually a little bit of what we call damming epoxy along the corners of the chip. This is so that when we create our wire bonds later on, we don't have any problems with the wire bonds touching the edge of the corner of the silicon and shorting out. We had some problems with that early on, so we paint this damming epoxy on by hand, and then we wire bond all the connections between the pads on the MEMS chip and the pads on the CPGA package. And finally, we fill in that gap with potting epoxy in multiple steps. So we put some in, let it cure, put some more in, and let it cure until we get a nice flat surface. And so we end up with about 100 microns of topology if you measure from the ceramic over this metal onto the epoxy, over the wire bonds, over the chip, and back onto the ceramic again. The total topology as you go up and down over those regions is about 100 microns or so. Our electronics are a little bit unique. We didn't want to have 64 preamplifiers for this array. It would make a very large piece of electronics. We'd have a lot of noise because every amplifier introduces noise, and we'd have a lot of outputs, which would be hard to handle. So instead, the scheme that the group came up with was to use an array of CMOS switches. You can see all the CMOS switch chips around here. And each of those switches is used, we use 3 of them on each microphone. So each microphone can either be switched to one preamplifier, switch to a second preamplifier, or switch to ground. So essentially this allows us to either reconfigure the array. So any microphone could be turned off if we don't want to use it, or routed to one output or routed to a second output. And in addition, we have a diff amp which sums these 2 outputs. So in the end, we have 3 analog outputs. All the microphones that are routed to preamp 1 here, all the microphones routed to preamp 2 here, and then the difference between those 2 signals here, so 3 analog outputs. And control of these switches is performed over a serial communication from a computer. And so if we reconfigure the array, we could take 2 measurements from 2 microphones that are nearby each other, and then we could do another measurement where you use 2 microphones that are far away, and so look at the difference in coherence between turbulent structures at close distances or long distances. We could make microphones that have kind of an interesting shape. So here's a stripe array, and here's another stripe array. So this kind of microphone would be relatively insensitive to fluctuations in the crosswise direction because they tend to cancel out, but more sensitive to fluctuations in the streamwise direction because there's a smaller spatial aperture in that direction. And you could then also move these apart. So you can think about this as kind of like two microphones where each microphone has a reconfigurable shape. So we could even do interesting things you couldn't do with large microphones, like make a ring microphone with another microphone in the center of it, which might be useful. So this is one way of thinking about how this array can be used. For calibration, we take the array, we flush mount it into the side of a plane wave tube, we set up plane waves that travel down this tube, and we have a reference microphone on the other side, and we compare the output of each microphone in our array to the output of the reference microphone. This calibration works well at frequencies below about 10 kilohertz, where the plane wave tube is small enough to have only plane waves propagating in it. So here's some example calibrations. The red curve is for a single element in the array compared to the dotted line, which is the theory of what the microphone should be doing. I haven't presented the computational model in this talk because I don't want to take the time, but if you look at our papers you can see that computational model. So we have a good model which predicts exactly what the microphones do. If you take all of the elements in the array, in this case we had 59 good elements, so 5 elements had been damaged in processing. 59 good elements, and sum them all together using our switches, then you get the blue curve. And so of course with 59 elements you have a higher sensitivity, with one element you have a lower sensitivity. And in both cases agrees very well with the expected output of the array. So we're able to calibrate here from 100 Hertz up to 10 kilohertz, and we get a nice smooth response. This little blip that you see here in the curve, this is because there's a null in the standing wave field which passes by the measurement location. So that's not a feature of the actual response of the microphone, that's a artifact of the calibration process. So really this curve is nice and smooth out to high frequencies. The resonant frequency of these microphones is somewhere around 300 kilohertz, so we expect this to be flat mechanically out to 300 kilohertz, although we can't calibrate that high in our acoustic setup. In terms of linearity, if we measure at a single frequency and just increase the sound pressure level up to high sound pressure levels, we see that the microphones are very linear. So even at 150 dB SPL, we see less than 0.5% nonlinearity deviation from linear. So these are very linear up to high sound pressure levels, which is good because in turbulence at high Mach numbers there will be high sound pressure levels. This is done at 1 kilohertz in the plane wave tube. We have been able to put these microphones into a turbulent boundary layer in collaboration with Spirit Air Systems in Wichita, Kansas. So they have a flow duct which has a 6-inch by 6-inch test section here, and this at the time that we went out to visit them, they were able to run up to Mach 0.6. I think now they're able to run up to higher speeds than that. And they have inline some diffusers, settling chambers, some vibration absorbing panels here, and some screens and so forth to try to make the flow nice and laminar when it first enters the test section, and then once it enters the test section here, the turbulent boundary layer starts to grow, or the boundary layer starts to grow and then becomes turbulent, and then we have our MEMS array mounted in this test section here, flush with the wall where it will be underneath a turbulent boundary layer. So the system is set up like this. The MEMS array is flush mounted, and we have some other things here, some Coolite transducers, B&K microphone, and an accelerometer. So here's a photograph of the setup. There's our electronics with the array on the bottom, and there's the top of the duct, and you can see some of the other wires here coming from the Coolites. And looking from the other side of the plate, there's the MEMS array flush mounted, and we put a little bit of modeling clay around the outside and razor blade that flat, so we have a nice flush surface. So here's our result we were so excited to see when we got to do our wind tunnel testing. Here we're looking at a frequency spectrum for single point measurement of the pressure spectrum that we're seeing from our array compared to the B&K microphone and one of the Coolites. And so the red is the MEMS, and the blue is the B&K, and the green are the Coolites. And you see in this mid-band from 300 Hertz to 10 kilohertz, we see great agreement between all three sensors. So that's wonderful. We're so happy to see that our microphones are performing very well. As we go up to higher frequencies, we see deviation between the three sensors. So first thing is that the Coolite starts to show higher sensitivities than the other two. This is, we think, because of the Helmholtz resonance of the Coolite mounting hole. So the Coolites are mounted in pinholes behind the plate, and so there's a spurious resonance that occurs because of that. So the Coolite is no longer actually measuring the real pressure because of the way it's been mounted, and so these two are still agreeing with each other and giving hopefully the correct answer. And then at higher frequencies, we start to see deviation between the B&K and the MEMS. At the higher frequencies, the wave numbers are becoming shorter and shorter. And so we believe that this is because the B&K is starting to become too big, and so it's starting to do some spatial averaging and other kinds of things here. And we're starting to see some results of the size of the B&K, which is maybe giving an incorrect answer, and hopefully the MEMS are still giving the right answer. But here this is really just, we're hoping that it's working correctly, but we have nothing to compare it to. So I guess all we can really say is that we see agreement between the three sensors up to about 10 kilohertz. And now we can start looking at interesting things. So let's say we do things with our array that we couldn't do with the other sensors. So let's do a measurement where we have a 2x2 array or a 4x4 array or a 6x6 array, so changing the number of microphones in the array. And so if we look at the spectrum as we do that, as we increase the aperture of the array, we see reduced output from the array for the larger apertures. And this makes sense because at high frequencies where there's a lot of fluctuation in the turbulent pressure in the spatial domain, as you increase your array, you get more and more spatial averaging and your measured pressure drops. So that makes a lot of sense and is an interesting measure of the spatial averaging effect for a microphone array in turbulence. Here's another thing we can do. We can look at two elements and look at the coherence between those signals and move those further and further apart. So turbulent structures are coherent over short spatial distances, but as the distances get larger and larger, there's more and more incoherence between the signals. And so this is exactly what we see. If we have two microphones that are one pitch apart, so about 1.3 millimeters apart, we see higher coherence, and then as we go to larger and larger distances, the coherence between those elements drops. So we have thought a little bit about how this wave number frequency spectra could be mathematically quantified. There are some pieces of work that we refer to, Majdanek and Jorgensen and Luptow. And basically, you get a measured pressure out of this array, which is the actual pressure modified by some sort of filter characteristic. And so there's this wave number filter, which depends on how you set up your microphone. So this wave number filter would have some spatial sensitivity function for an individual element multiplied by some phase shifts here, and then the state of each element, whether it's switched to -1, 0, or +1. And so by changing these, by reconfiguring the array, you can produce different wave number filters and therefore get a different measured pressure output for an actual pressure. And since this depends on wave number, by reconfiguring the array and getting different wave number filters, you should be able to extract information about the wave number characteristics of the actual pressure spectrum. So here's some examples. Let's say I just put 4 microphones here and turn them all on and turn everything else off. I'll get a wave number filter that looks like this. So it has a high output for small wave numbers, close to, here's 0, 0 in the middle, for close to 0. So as long as the wavelengths are long, then we just get our one output. But as the wavelengths get shorter and shorter, so the wave numbers get higher, at some point you get fluctuation across this aperture, and then the signals cancel out and your sensitivity drops. So this basically gives you this kind of uniform symmetric filter which amplifies low wave numbers and attenuates high wave numbers. Here's another one. Let's say we did a checkerboard pattern. So we turned every element 1, +1, -1, +1, -1. Now what we get for our wave number spectrum is that at certain wave numbers we get a large amplification and everywhere else attenuation. So what happens is if the wavelength matches this pitch, then you get sort of like constructive interference. You get a large signal from all the microphones that are in the right phase to add up to something positive. And so when the wavelength matches the pitch, you see these peaks at those particular wave numbers, and everywhere else you get attenuation of the signal. Your turbulent pressures from your acoustic pressures that are present. Your acoustic region lies at a particular circle in wave number space. It would be a circle if there's no flow. It's a little bit elongated if there's flow, because everything travels at a fixed speed, at the speed of sound. But your convective energy is traveling at a different speed, and so if you set up your wave number filter correctly, at this frequency anyway, you're gaining up your convective term, your turbulent pressures, and you're attenuating your acoustics. So if you wanted to pick turbulence out of an acoustic pressure, then something like this might be useful. So we have more work to do on this, but this is the idea of our wave number filter. So in conclusion, thank you very much for listening to this rather lengthy presentation. We have demonstrated a MEMS acoustic array on a chip with 0.6 millimeter diameter elements, 64 elements on a chip, 1.25 millimeter center-to-center pitch. We can operate from 100 Hz to greater than 40 kilohertz with a 10 volt DC bias. We have a dynamic range of 60 dB SPL to greater than 150 dB SPL in a 1 Hz band. And we have a unique switching electronics configuration that's scalable, does not require a large number of preamplifiers or DAC channels, and that switched array can act as a reconfigurable wave number filter. We have done some wind tunnel testing, tested up to Mach 0.6 and 38 array configurations. We're able to distinguish turbulence from other signal sources such as structural vibration and acoustics in a band from 1 to about 10 kilohertz, depending on the Mach number. And I didn't show this data in this presentation, but we have done some analysis to try to remove acoustic contamination, structural vibration from our signals, and then compare our turbulence measurements to some turbulence models in the literature with good results. So we'll be continuing this work to do more analysis of our turbulence data, hopefully take some more data at higher Mach numbers and continue to improve the array. Thank you for your attention.